Good afternoon, everyone. Thank you for joining in. Today, we're very happy to have Dominik Neuenfeld from Perimeter Institute, and he will tell us about holonomy constraints in double holography. So please, Dominik, take it away.
All right, thanks, Hugo, and thanks for the invitation. I'm happy to be, at least virtually, like all across Europe, so that's nice. I hope that everybody can see the slides well. Right. So yeah, as Hugo mentioned, I'm going to talk about double holography, and in particular, I'm going to sort of review holonomy constraints, or well, different choice of holonomy constraints you can choose for computing RT surfaces. And what I'm going to talk about is mostly based on this paper down here, which appeared on the archive in May, and then of course in turn is based on a whole lot of other papers. Again, from this year, and then work from last year with Vincent Chen, Rob Myers, Ignacio Reyes, and Josh Sander. Just generally, I'm super happy to being interrupted during the talk. So please, if you have any questions, feel free to do that. I'll also stop on the way to perhaps like give some time to ask questions. Okay, so let me maybe start with some sort of generic broad motivation. And that is that in physics, and in particular, sort of in the realm of quantum gravity, where my talk's going to be located in, we're interested in computing entropies. And generally, how this works is we have some system of interest, and we pick a subsystem, which I've denoted here by A. We build the reduced density matrix by tracing over the complement of A, and then we can compute the quantity, which is called the von Neumann, or sometimes the entanglement entropy, which is given by minus trace rho A log rho A. And it's useful for a lot of purposes, but here in particular, we're interested in it because it's a diagnostic for the lack of information. So as a super simple example, we know that if the von Neumann entropy is 0, that the state described by the density matrix rho A is pure. Now, as many of you know, there's recently, and by recently I mean over the last 2 years, been the proposal for a novel method to compute entropies in theories where we have semiclassical gravity, and that again goes by various names. I'll call it the island formula for the purpose of this talk. And the way to compute this entropy, which I will call the island entropy, in the literature you'll find names like fine-grained or quantum gravitational entropy, is a bit more complicated, and it works as follows. So instead of just focusing, if you want to know the entropy of some region A, instead of focusing just on the reduced density matrix of the region A, we are considering bigger subregions, but we also include other subregions, which I will call I here, I for island. And then we compute the following island functional, which is the von Neumann entropy of the quantum fields on the region A union I, plus the area of the boundary of I over 4G Newton. And then we looking for extrema of this functional, and if they're multiple extrema, we'll take the minimum, evaluate the functional on that minimum, and they will give us this island entropy. Now, one extremum we will always find is the one where the island is empty, and then the whole thing reduces to the usual von Neumann entropy. But then in some situations, it might be that there's a second extremum, which also might be minimal. Or we have a non-trivial region I we need to include to get the correct island entropy. Of course, you might wonder, why are we interested in another measure of entropy? What's wrong with the von Neumann entropy? And so the main motivation for this formula stems from the fact that, in a sense, quote unquote, it solves the black hole information paradox, in a sense that I'll make clear in a second. And I'll just kind of like super briefly talk you through how this works in the case of an eternal ADS black hole coupled to a bath. Usually people are familiar with the black hole information paradox on an evaporating black hole, but in fact, there's a similar paradox for an eternal black hole in ADS, a large ADS black hole, if we couple it to a bath. And how this works as follows. Here I've drawn a Penrose diagram of the eternal ADS black hole, and I make its boundaries transparent, couple it to bath regions. One, I couple to the left exterior here, one I couple to the right exterior, and then I bring the whole system in the Hartle-Hawking state. And the Hartle-Hawking state has a particular entanglement structure. Namely, we have, for example, two right moving modes here. So we have one in the left exterior, and that mode is entangled with a right moving mode in the right exterior. And similarly, modes in the baths are entangled. So we could have, say, a left moving mode in the left bath, which would be entangled with a right moving mode in the right bath. And what we can ask now is, what is the entanglement entropy of the radiation system of the bath here? And one thing we realize directly from this t = 0 slice is that those modes I've drawn here, they don't really contribute, right? So either the pure state of these two entangled modes is either completely contained in A or is completely contained in the complement of A, so we don't get a large contribution. However, if time runs forward and we look at the bath at some later time, what we see is that, well, take, for example, these right moving modes here. One mode will have fallen into the black hole, the other one will have escaped into the bath. And so if you compute the reduced density matrix of those modes by tracing out the complement of A, then this mode here will be in a mixed state and will contribute to the entropy. And then it's not hard to convince yourself that as time goes forward, this happens for more and more modes. And what one finds is that the entropy of this region A grows linearly. Now, that's not like a priori, that doesn't seem to be a problem. However, it becomes a problem if we insist on sort of the interpretation of our ADS black hole as having e to the s, whereas the Bekenstein-Hawking entropy microstates, because in that case, the black hole, or like this part of the space-time, can only be entangled by a finite amount with its complement system. And since we're in a pure state, it needs to purify the state of the radiation, but it can only do so if the entropy of the state of radiation is below 2 times S naught, so 2 times the Bekenstein-Hawking entropy, essentially because we have the left and the right exterior. And so we see that at this point, this maximal amount of entanglement, which is available to the black hole, gets violated. And so there's sort of 2 ways out. Either the black hole isn't really, doesn't have e to the s naught available microstates, or unitarity of time evolution fails here, and the pure state we started with turns into a mixed state. Now, this, of course, well, that's what we not want, right? And so the island formula solves, again, in quotation marks, this problem by enabling us to produce something which is called the page curve. And if we use the island formula now to compute the entropy of the bath, then initially we're in the situation we were in before. The dominant extremum gives a rising amount of entropy up to some time, which we'll call the page time. And then after this page time, another saddle point takes over, where we have an island which spans the complete interior of the black hole and just sits outside the horizon. And you see in this picture here at this late time, we have, again, this green pair of entangled modes. And now they do not contribute to the von Neumann entropy part down here, because one of the partners is encoded or is contained in the island, and the other one is contained in the region A. However, we do pay this penalty factor of the area of the boundary of the island, which I said just sits outside the horizon. So this area is the horizon area of the black hole horizon times 2, right? Because we have 2 exteriors over 40 Newton. So this gives us 2 times the black hole entropy, and the island entropy then follows the minimum of either the rising curve we've seen on the previous slide, or this 2 times S naught curve, which is given by the other extreme of the island formula. And so we find that the entropy rises initially and then saturates, and we have a non-trivial island. And so, right, so that's the role of the island entropy. It enables us to derive this page curve. And there's even more claims, namely that this island I is somehow encoded in this in the radiation region, the bath A. And so I will talk about this later. But now the you might say, okay, that's all very nice, but clearly that doesn't really explain the like whole information paradox, and it really opens up many more questions, right? So in fact, in quantum field, if we do QFT in curved space-time, we find that the state outside the black hole is mixed, and in fact, its von Neumann entropy, or the entropy we usually use the von Neumann entropy, just keeps on growing. And an obvious question is, well, what's wrong with actually using this entropy? So why is this the wrong why would this be a wrong computation? And then some people might say, well, there's a very nice interpretation in terms of the gravitational path integral. If you compute the entropy using the replica trick, you need to include some non-trivial gravitational saddles, and that's certainly true. But I think that still doesn't really answer the question. What I think we would really like to have is some Hilbert space perspective on why shouldn't we be using the phenomenon entropy. And the second question is, well, how is the island even encoded in the radiation? In particular, if we just use standard semi-classical gravity, that there doesn't seem to be any information contained in the radiation. So how could it be that the interior of the black hole somehow is encoded in this radiation? But assuming that those things are right, assuming that there's an issue with the phenomenon entropy and that the island is somehow encoded in the radiation, then the question becomes, well, what really is semi-classical gravity, in particular in high dimensions? And there's a lot of work in the literature where people think about what semi-classical gravity is, in the sense that it's certainly not simply a low energy effective theory like we're used to from QFT, but it has some of features. Could be an ensemble average, there could be some coarse graining involved in the definition. There's also this idea that semi-classical gravity is, in a sense, some low complexity approximation, such that it's not a faithful, or it can't be used to faithfully answer questions asked by observers with an exponentially computational power. Okay, and the proposal, the idea here of this talk is to use double holography to sort of try to make progress on these questions and put this a bit into perspective. All right, so if there are any questions, that would be a good time. Otherwise, let me give you the outline of the rest of this talk. I'll first review the idea of double holography very briefly. Then I'll talk a bit about computing entropies in double holography and revisit the RT constraints and suggest sort of a rule for which RT constraint to choose to compute what. Then I'll discuss the consequences of this proposal and sort of try to bring this point home by then showing you a qubit toy model, or maybe two if time allows, before I end with a few remarks on what happens if we take those lessons I think we can learn from double holography and try to apply them to semi-classical gravity and quantum gravity sort of in the real world in 4 dimensions. All right, so what is double holography? Double holography is essentially putting two dualities or two models together. The first model is known as the ADS BCFT correspondence. And the idea here is that we have a boundary conformal field theory. So all those pictures show time slices. We have a boundary conformal field theory on some ambient space here, and that might be coupled to another quantum mechanical system at its boundary. And this sort of, like an ADS CFT, the CFT serves as the UV complete description of our theory. Now there's a dual description of the system, which is given by an asymptotically ADS space in 1 dimension higher, where the asymptotic boundary is conformally related to this ambient space of the BCFT. And then there is an end of the world brane, which intersects this space, cuts off part of the boundary. And the point where it intersects the boundaries is exactly where, in the BCFT description, my quantum mechanical system will live. This brane, for like practical purposes, is modeled as a constant tension brane. So that would be the action. And we choose Neumann boundary conditions at the brane. The motivation, or one of the motivations here being, is that we can, maybe not the motivation, but the effect of this is that as we tune the tension of our brane, we can move the end of the world brane up and down. And we'll be interested in a situation where we increase the tension up to some critical value such that it sits very close to where the other part of the asymptotic boundary would have been. In the BCFT description, that corresponds to the limit where there's a large number of degrees of freedom here, and the boundary degrees of freedom. And in this limit, a third description now becomes available. To sort of tell those apart, I will call the BCFT description the boundary perspective, the bulk, this ADS bulk description, the bulk perspective, and then this new description, the brane perspective. And in this brane perspective, what we find is that we have a conformal field theory in d dimensions living partially on a fixed background, but then the matter fields can cross into a region which has the geometry of the end of the world brane and where it is coupled to gravity. And what I will be mostly interested in, so how to transition between the boundary and the bulk perspective is known reasonably well. Between the bulk and the brane perspective is known, I would say, less well. So this is originally work based or like based on work like Harch and Randall. But I think what's really the interesting part here is the duality between this boundary and the brane perspective, and that's sort of can be pieced together by taking rules going from the boundary to the bulk perspective and bulk to the brane perspective. But that has been so largely left unexplored. Okay.
Excuse me?
Yeah.
Can you go one slide before? So this C of boundary, the boundary degrees of freedom is the degrees of freedom of the quantum system, right?
Yes, yeah.
Like, what is the reason that you want it has more degrees of freedom than the BCFT's degrees of freedom?
Right, so the intuition is that if I go to this limit in the boundary perspective, then the end of the world brane gets really close to this, this dotted line here, which is where the asymptotic boundary would have been. And in this limit, what happens, and I maybe should have said this a bit more explicitly, one of the graviton modes in the bulk will essentially, what's called locally localize to this brane. And that enables me to have this additional perspective where two things happen. A, I have gravity on here, and in this particular limit, this gravity theory will be well approximated, at least to leading order, by Einstein gravity, and then there's going to be higher curvature corrections. And I will have the conformal field theory living here, which has a UV cutoff, but this UV cutoff will be very high compared to the curvature scale of the background.
Okay, I see your point. But so actually your BCFT degrees of freedom doesn't contain this like two green dot or two green box.
Well, the whole thing here would be called the BCFT. So it's the point is, so if you want a stringy construction of those systems, there's been like nice recent work by Mark van Ramsdijk and a grad student of his, Chris Waddell. How you can think of this is a stack of D3 branes you would use for standard, n equals to 4 super Yang mills and ADS 5 process 5 holography, and then you let them end on sort of like a stack of NS5 and D5 branes, and you stretch some D3 branes between them. So there's essentially an n equals to 4 super Yang mills locally in this region, but then there's a codimension 1 locus, like here in this picture there are two, where additional fields are localized.
Okay, yeah, I understand the picture. I think you exclude the additional degrees of freedom from your boundary CFT. That's why you have like more dense fields on that green box. Like the fields are denser in these green fields than on the half circle.
Yeah, I mean, you just add sort of like, you take a codimension and you just like locate it at the boundary, and you add some interaction between. You could start with the BCFT here, where nothing happens on the boundary. You have just like standard boundary conditions. And then you take another codimension 1 system, you put it where the boundary is, and you introduce some interaction between the two systems.
Mm-hmm. Okay, thanks.
All right, thanks for the question.
I have another brief question. Does the end of the world brane back react on the asymptotically ADS geometry?
Right. So when I say that you increase the tension and then the brane goes up to the asymptotic boundary, that's in fact is a back reaction effect. So you could also say the end of the world brane to like sits at the center of ADS, and because it's heavy, it back reacts and creates much more volume. And like going to a different coordinate frame, it just looks like it's moving outwards. So these are really the same effects.
Okay, thanks.
Thanks. All right, so the other thing we need to do in order to discuss islands, we need to introduce a black hole into our system. And the easiest way of doing this is look at the bulk perspective, but now in ADS Rindler coordinates. And the boundary perspective, what this translates to is we have, we cut our BCFT in half along this dashed line and take those two pieces and bring them in the thermofil double state. And in the brane perspective, what we have is We have a black hole here with like an eternal black hole here on the brane. It's a massless topological black hole with a horizon here indicated by this dashed line. And each exterior is coupled to some rigid region, which I'll call the bath. And so this is really the picture we've had before now, just a time slice where the black hole paradox happened and where we have a black hole which is in thermal equilibrium with a connected bath. And here I've tried to draw sort of like also the time direction. Here we have the two BCFTs with the additional boundary degrees of freedom here, and they're both entangled. And this here is just the Penrose diagram of our eternal ADS black hole coupled to baths. All right. So now let's briefly see how we can compute the page-Griffin double holography. First of all, why did we go through all this this work? Why would we use double holography? The nice thing there is, as with generally holographic theories, that difficult questions can be answered by slightly easier computations. In particular, here we can compute the entanglement entropy by a geometrical bulk computation. So we can use the RT formula, which tells us that if you want to compute the von Neumann entropy of a region A, we are looking for a bulk surface which extremizes its area functional. And if there are several extrema, again, we use the minimum, and then there's higher order corrections, which I will ignore for the purpose of this talk. Now, and the second point which we'll see is that also double holography allows us to talk about sort of where information is located, but that will hopefully become clear in a moment. Now, the point here is if we are using the RT formula in ADS BCFT, then the usual homology constraint, namely that our bulk RT surface needs to be homologous to the region A we're interested in, is slightly relaxed. What we find is that the homology constraint now is that the RT surface only has to be homologous to A up to terms which are contained in the end of the world brane, which I've denoted up here by X. And oftentimes that's sort of interpreted as saying with end of the world branes, well, whenever end of the world branes, the homology constraint has to be modified. And in part of this talk, I will sort of discuss, hopefully convince you that this is maybe not the exactly correct way of thinking about this. In practical terms, what happens now with this real X homology constraint, if I'm interested in some region A here in the bath, which is some fixed distance from my boundary degrees of freedom, and then instead of having just one choice, the usual choice I would expect from global ADS, namely this RT surface, I have a second RT surface which connects up to the brane, and I will have to choose the smallest of those to compute the von Neumann entropy of the region A. And so initially, this surface here dominates. Its area grows linearly, so I get this rising curve here. And then at some time called the page time, this phase here where I have an RT surface which connects to the brane will dominate. This is time independent, so I see what I've seen before, the saturation of the von Neumann entropy. And even more than that, I can reinterpret the area of this bulk RT surface in a particular way. Namely, I can write this as a large contribution coming from close to the brane, which you can show is the area of the boundary of I/4 G Newton on the brane, plus the correct higher curvature corrections to this area term from the wall-Dong entropy. And then sort of the bulk part here of the surface looks, and that sort of intuition then from ADS CFT, like the entanglement of quantum fields in the region A, including the QFI divergences coming from this region, and quantum fields in this region, which I called X before, which I call now I because it plays the role of the island in the brane perspective. Secondly, the bulk externalization procedure of the bulk RT surface is really the brane island formula. And then thirdly, this picture also suggests why and how the island is encoded in A, namely this region up here, if this is the correct RT surface, sits in the entanglement wedge of A. And the entanglement wedge of A is the region enclosed by A and the RT surface, which is encoded in the CFT within the region A. All right, so all of this seems to suggest that, okay, so we've computed von Neumann entropy and we got sort of the island formula back. So maybe the von Neumann entropy of A is just the island entropy of A and we're done. But I think here one needs to be careful. So what we've done really is we've computed the Neumann entropy in the boundary perspective, and then we reinterpreted, or like using rules from ADS BCFT, and then we reinterpreted the result in the brane perspective. And so one thing we can say for sure is that the island RT surface computes the Neumann entropy of the region A in the boundary perspective, but it's not necessarily clear that it also computes something like the Neumann entropy in the brane perspective. And so that sort of brings us to a question. We've seen that in the brane perspective essentially looks like the semi-classical picture we used to working with. So the question somehow becomes, can we make the brane perspective just behave like semi-classical gravity, or can we treat this, or does it play the role of semi-classical gravity while still having these RT surfaces, or which I will call the island RT surface? And I will argue now that this leads to a contradiction. So what I'll assume is that the brane perspective is really some semi-classical quantum mechanical theory. And in particular, what I mean by this is that there's local degrees of freedom everywhere here on the brane and in the bath, like I used to from doing semi-classical physics. And then secondly, I'll assume that there's some sort of holography going on, namely that there's some unitary map from the code subspace in the bulk to some subspace or some code subspace in the brane perspective, which I call H brane here. And what I really only need are two things. First of all, pure states in the bulk map to pure states on the brane. So there's no cloning. So pure states map to pure states. And then second, that there's no cloning. So that information, which somewhere in the bulk doesn't appear like in two separate locations on the brane. And then the second thing I will use are standard rules of entanglement wedge reconstruction, which are known from ADS CFT, and of course not proven in all those more general cases I'm discussing here. But since entanglement wedge reconstruction sort of has led us to the RT formula and to the island formula, it seems reasonable to also assume them here. So in particular, I will use entanglement wedge complementarity, which essentially means that if I can reconstruct something in the region A, like some bulk information in the region A, then I cannot reconstruct it into A complement. And second, entanglement wedge nesting, which is just another way of saying that if I cannot reconstruct something in A, then I certainly also cannot reconstruct it in some subregion of A. Okay, so making those two assumptions, I'm naively led to a contradiction with the existence of those island RT surfaces. And the argument is very simple and goes as follows. So assume I have some local operator up here very close to the brane state, but inside my entanglement wedge of A. Then clearly it's not in the complement of the entanglement wedge of A. And by entanglement wedge complementarity and the fact that my state is pure, the complement of the entanglement wedge of A equals to the entanglement wedge of the complement of A. So that means that I shouldn't be able to reconstruct phi from the complement of A. But now in the brane perspective, what is the complement of A? Well, I've assumed that I have a local semi-classical field theory with local degrees of freedom everywhere. So in fact, all of this up here, I think of as being independent of the region A. So A complement really is the rest of the bath here, plus the whole gravitating region. And by entanglement wedge nesting, that means that in particular, I shouldn't be able to reconstruct the operator phi from the region B here, which is contained in A bar. Now, the problem though is that it seems I can do this. And the reason is that there is an extrapolate dictionary as I go to the brane. So I can relate the asymptotic, well, not asymptotic, but the behavior of bulk fields as I go to the brane to fields on the brane. And then I should just be able to use HKLL, so a standard bulk reconstruction technique, which solves the equation of motion at least a tiny bit inwards from the asymptotic boundary to just reconstruct this operator phi here, provided it's close enough to the brane. So what I've argued in brief is that I have an operator phi here, which I can reconstruct from A, which means I shouldn't be able to reconstruct it from anywhere on the brane, but practically speaking, I've argued that, yes, I can do this. And so we have a contradiction. So what do we do with this contradiction?
Sorry, Dominic.
Yeah.
I have a question here. While you say phi, a bulk field can be reconstructed from this region, it means, okay, if it's asymptotic region, like on the asymptotic ADS, then I understand that we can reconstruct with some CFT operators, right? But here it's like reconstructed from what on B?
Well, there's still CFT operators here, right? So in the brane perspective, there's two things. There's a matter field, so it's the same CFT that lives on the asymptotic region, which is also allowed to, like, excitations are also allowed to go onto the brane. So the same CFT, and now with the cutoff, also lives on the brane. And then secondly, there's additional modes, which, for example, play the role of the graviton, or that could be dynamical sources. And so I can reconstruct similar operators, or like I can reconstruct operators near the brane. Again, in a similar way, I can do this in the asymptotic region, just from the fields on the brane, and then perhaps I also need to include, depending on which field I want to reconstruct, dynamical sources.
So you are saying that we have some local CFT data also on the green slice.
Oh yeah, sorry. Yeah, I should have maybe emphasized this before. Yeah. So in the brane perspective, what we have is a CFT which lives on the whole geometry. So on this asymptotic region, but also on this brane geometry, except that the only difference between those two regions is that here I have dynamical gravity as well.
Okay. And we also need to use the dynamical data of the gravity on the.
Yeah, it depends a bit on what you on what you want to reconstruct. So depending on your bulk field, it might be that you get a new mode on your brane, which describes now a dynamical source. And so if that is the case, you will also have to include this dynamical source in the reconstruction procedure.
Okay, thanks.
Thank you. Okay, so, well, what can we do? We can either drop some of our assumptions, or what I will argue for, and this is sort of like the upshot, or I'd say like the most important slide of the talk. So if you keep anything in mind, let it be hopefully this slide here. We can instead just be careful about the homology constraint we're choosing. And so the proposal here is that in order to compute the von Neumann entropy of some region A in the bath, we use the RT formula with one of two homology constraints. Either we're in the boundary perspective, so with ADS BCFT, and we use the homology constraint that Takayanagi has taught us to use, namely the RT surface only has to be homologous to the region A up to subregions on the brane. But if we're in the brane perspective, then we just choose a stronger homology constraint, and here we don't allow the RT surface to end on the brane. Now, what this does for us, it sort of bans or forbids this RT surface in the brane perspective, and thus solves the contradiction I've shown in the previous slides. The other thing that does is that I mentioned before that sometimes people read the homology constraint as if we have end-of-the-world branes, we need to choose a different homology constraint. But what I am arguing for is that if we're doing computations in the boundary perspective, we're using a different homology constraint. But in the brane perspective, we really treat the end-of-the-world brane as essentially part of the boundary and use the standard ADS CFT homology constraint. And yeah, so again, practically speaking, in the boundary perspective, what this means is we have two candidate RT surfaces, and in the brane perspective, we have only one candidate RT surface. So what are the consequences of this proposal? Now, the first and obvious consequence is that after the page time, the von Neumann entropies in those two pictures differ, right? We've discussed this before. In the boundary perspective, initially, I have an RT surface which sort of caps off the region A. The same is true in the brane perspective. And then after the page time in the boundary perspective, I have this phase transition. But because I don't have the second candidate surface available in the brane perspective, I cannot have this transition. And instead of the growth of the entropy saturating, it just keeps on growing linearly. Now, this behavior is really reminiscent of the behavior of semi-classical gravity. So if you were to do the computation in semi-classical gravity and just compute the phenomenon entropy in semi-classical gravity, that's exactly what we would find. So how can this be? The nice thing about double holography is it immediately tells you how this can be. Namely, what we learn is that the bulk state or parts of the bulk state are differently encoded in those two pictures. So before the page time, the region A in the brane and the region A in the boundary perspective both encode the shaded part here of the bulk. However, after the page time, in the brane perspective, it's still the same shaded part of the bulk which is encoded in A. However, in the boundary perspective, there's a much bigger region up here, which is now encoded in addition. In sort of words which have been used in the literature, this A here in the boundary perspective also encodes what's been called the Python's lunch. And I will have a bit more to say about this in a second. Whereas in the brane perspective, it really encodes sort of like a quote unquote simple state. This part of, or like part here of the lunge, which is not encoded in the region A, would then in the brane perspective instead be encoded in local degrees of freedom living in the gravitating region. To make this maybe a bit more precise, let's look at operator reconstruction. And in order to do this, I will split the operators into two separate classes. One class I will call simple operators, and simple operators are all bulk operators which live in this region down here, the region which is called the outer wedge, so the region outside the outermost extremal surface. And then I will define complex operators as local operators, which live in the lunge. So this is inside the entanglement wedge, but not in the outer wedge. So that's this region up here. The reason for this name, for these names, is essentially the Python's lunge conjecture and the inverse Python's lunge conjecture. And here the claim is that simple that operators in this region down here, so in the outer wedge, are simple operators because the reconstruction, if you were to write down a quantum circuit to do this for you, that would scale polynomially in, whereas operators here in the lunge, like the size of the quantum circuit, would scale exponentially in. And so these would be very complex, very hard to reconstruct, whereas operators down here in the outer wedge would be very simple to reconstruct. And so what we see here is that simple operators in the brane and in the boundary perspective can both be reconstructed into A. And in this particular example, if they're close enough again to the boundary, we can just use standard HKLL techniques to do so. So really these operators are like the boundary representation of those two operators would be the same in the boundary and in the brane perspective. However, this complex operator up here, which lives in the lunge, in the boundary perspective, can be reconstructed into A, whereas in the brane perspective, I would have to reconstruct this into the gravitational degrees of freedom on the brane. The important upshot here is that operators in the island, so operators very close up here, are accessible from the bath in the boundary perspective, but simply not in the brane perspective. And so since the brane perspective sort of plays the role of semi-classical gravity, you might be tempted to say information about the interior of the black hole is simply not accessible in the radiation, just in the semi-classical formulation. Okay, now, so these are the immediate consequences. But I mentioned before that there's, due to this, this list of sort of dualities, there is a relationship between the boundary and the brane perspective. And at least in some part of the Hilbert space, we expect there to be a duality. And then a natural question is, okay, so if the phenomenon entropies are different in those two situations, is there a way of doing a computation in the boundary perspective which computes the phenomenon entropy of the brane perspective and vice versa? And in fact, there is. The simpler of the two is just computing the phenomenon entropy of the region A in the boundary perspective from information in the brane perspective. And we already know how to do this, right? Because what we've seen is that this particular RT surface can just be reproduced by using the island formula. Now, it's sort of like, I guess, important, and let me just like emphasize this, right? The interpretation here is, I feel like slightly different to what one usually sees in the literature. And the interpretation here is that the von Neumann entropy in the boundary perspective is dual to the island entropy in the brane perspective. Or in other words, the island entropy in the brane perspective doesn't necessarily have an intrinsic meaning. It gets an intrinsic meaning if I tell you that there's a different duality frame, which I've called the boundary perspective, and that computing the island formula in the brane perspective is dual to computing the von Neumann entropy in the different duality frame. Of course, naturally, I can turn this around and ask, is there a way of computing the von Neumann entropy in the brane perspective, but now from data in the boundary perspective? And there is, and to understand how this works, we just need to realize that the brane perspective von Neumann entropy here is computed by the area of this extremal surface, which happens to be the RT surface. I'm just focusing on times after the page time. In the boundary perspective, that surface, this extremal surface, still exists. It just happens to not be the correct RT surface, but a non-minimal extremal surface. And so the question becomes, what's the boundary interpretation of non-minimal extremal surfaces? And luckily, this question in a slightly different setup has been asked by other people, in particular, Meta Engelhardt and Aaron Wall, and Engelhardt, Pennington, Shahbazi Moghadam more recently. And without going into too much detail, what they argued is that the area of this outermost non-minimal extremal surface is associated to, or computes, what's called the simple entropy. Now, the simple entropy is a coarse-grained entropy in the sense that it's the von Neumann entropy maximized over an ensemble of different states, which correctly reproduce particular one-point functions in the case of particular sources. Or again, just in brief, it's a coarse-grained notion of entropy. So the upshot of this is that the von Neumann entropy in the brane perspective is dual to the simple entropy, which is a coarse-grained measure of entropy in the boundary perspective. All right, so let me give you some intermediate summary. The brane and the boundary perspectives, as I tried to argue, are related by some sort of duality. And this duality takes the following form. For simple observables in the bath, and that's the only thing I've really discussed, questions about the bath, this duality is trivial. So they're just the same in both the brane and the boundary duality frame. However, if I want to compute complex observables and see how the duality acts on them, then it involves one of two things, either non-locality or coarse-grain. Non-locality appears if I have something in the boundary perspective, say a von Neumann entropy, which I want to compute from the brane perspective. So one example would be computing the von Neumann entropy of a bath subregion A in the boundary perspective. This can be done in the brane duality frame by computing the island entropy. But this, of course, involves some non-locality because the von Neumann entropy in the boundary perspective of the region A just depends on the region A. However, the island entropy of the region A depends on much more, right? It depends on the global state, it depends on the global geometry. So this is highly non-local, and similarly, we've seen that for complex operators which are encoded in the region A, we can also reconstruct them or measure them from the brane perspective. However, we might need access, or we will need access to the gravitating region, and not only to the region A. And then the other way around, we've just seen the example. If we want to compute the von Neumann entropy in the brane perspective by doing a computation in the boundary perspective, then we've seen that this computation involves some coarse grain. So the other upshot, which I think is quite interesting and important, is that what we see here is that information about this island is accessible in the bath, but only in the boundary perspective. From the point of view of the brane perspective, the information about the island and so on is just not isn't encoded in the bath, but instead it's just encoded in local degrees of freedom in the interior of my black hole. All right, so that would be a good moment to take some more questions if there are any. And since there are none, then let me try to take or drive this point home by introducing a small qubit toy model, which sort of captures the main idea. So here, the physical setup I want you to think about is slightly different. Imagine that you create a black hole by collapsing some pure state of matter, and you let it completely evaporate, and now you're left with radiation. And the claim then, or the idea then, is we have two different descriptions of the same system, two duality frames. One, which is sort of equivalent to the boundary perspective, and which I'll also call the boundary perspective for this toy model, as it's just some Hilbert space of my radiation with n qubits, and I will generally denote this by these blue boxes. But then there's this other duality frame, which is the brane perspective, and that's the semi-classical picture of an evaporating black hole, which contains two pieces. One, again, is the space-time in which my black hole evaporated and where it left its radiation. But then there is the baby universe created by the black hole. So the black hole sort of like splits off from the space-time and creates a baby universe, which also has its associated Hilbert space. And now the claim is that there's some, or the idea is that there's a map from this sort of like boundary perspective where I only have radiation, a pure state of radiation, to this other brane perspective where my physics is described by radiation plus a baby universe. So what we do now is we consider a pure state in the boundary perspective, and I also assume that this radiation Hilbert space is smaller, or at least not bigger than the black hole interior, the baby universe Hilbert space here. And then I define this map U between those two systems by a two-step procedure, which is sort of motivated by double holography. First of all, I take the radiation and I embed it into the radiation part in my brane perspective. And then I just set the black hole interior to some reference state, doesn't really matter. And then I just scramble the whole system with some random but fixed unitary. So I take, essentially what this does, it takes the radiation information here and smears it across the whole system. Now what I can do now is I can ask the same questions I've asked before. So I can take some subset of the radiation and I can compute its von Neumann entropy in this very simple qubit model and plot this as a function of how much of the radiation I'm considering. So I define the subset A here of size m. And what you find is, if you do this, that the von Neumann entropy, as I increase the size of m, initially starts increasing until m is n over 2, so it's half the radiation, and then it goes down again. So we get a page curve, like we also did by computing the von Neumann entropy in the boundary perspective in double holography. Now I can do the same thing, but now in my brane perspective equivalent. And what I find there is that the von Neumann entropy just keeps on rising until m is equal to n, where I've now considered all the radiation. So the von Neumann entropy of the full radiation is just some large number and doesn't turn back down. So what we find is sort of like the same picture we've seen before. We have two different von Neumann entropies for the same subregions. And the second note here I want to make is that simple observables in this model trivially agree, basically because we're in a maximally mixed state, and simple observables would be observables which only act on one or two sides, maybe. And so the quantum state on very few number of sides is just given in both cases by maximally mixed density matrix. Okay, so the question is, can I now devise some formula which correctly reproduces the von Neumann entropy in my boundary perspective from a computation I can do in the brane perspective? And I can do this by defining what I call the island entropy now for this qubit model. And that's defined by considering the von Neumann entropy of the subregion A union I, where I is any subregion of the black hole interior, And then I minimize this entropy here of A union I over all possible choices of I. And now if you use this definition to compute the island entropy in the brane perspective, what you find is that initially, again, the entropy just keeps on rising linearly. And there's no benefit you gain by including some non-trivial island. So the minimum here of this function of the phenomenon entropy here is just given by just taking the reduced density matrix on your subsystem down here. But right, but once A becomes bigger than half of the radiation subsystem, then it suddenly becomes beneficial to include an island in the black hole interior. And in fact, the island you want to include is just including the full black hole interior. And what you see then is that the island entropy, if m is bigger than n/2, so half the radiation size, turns down and follows a page curve. Right, and again, the point here is that this functional here I've just made up. Right, this has no sort of like intrinsic meaning in a quantum mechanical system which consists of m or like n plus k qubits. But it becomes, or it gets an intrinsic meaning if I realize that, hey, I can use this to correctly reproduce the von Neumann entropy in my original system, and so that played the role of the boundary perspective. And then there's a similar. How much time do I have left?
So you started about 5 minutes past 3. So roughly 10, but we can give you 15 minutes, I think.
No, that's fine. I think like 10 should be perfect.
Okay.
All right. So and there's a similar computation you can do with in this qubit model, which is sort of like reminiscent of introducing wormholes into your setup. So usually wormholes appear when we do replica computations in the Euclidean path integral, and doing like replica computations in this setting here seems very hard. So let's do something much simpler. Namely, we just consider the purity that's also sort of been used as a proxy to show that there are wormholes in this paper by Pennington, Schenker, Stanford, and Yang. And so purity is just defined as the trace of rho squared. And so again, we pick rho to be some in the radiation system to be some random but fixed state. And we can then compute the purity by using some Haar random formulas down here. And what we find is that the purity as a function of the size of the subsystem you consider follows this functional form here. Initially, the purity is high, essentially because you either have no qubit or like one qubit, which is just in a mixed state of 1/2 up, 1/2 down. And then as you increase your system size, your system becomes less and less pure, if you will, until when you consider your whole system, you have a pure state and the purity goes up again. In formulas, we find that the purity is 1/2 to the m plus 1/2 to the n minus m, where n is the total system size and m is the sort of like window of consideration. And then again, I can apply my my map U here and map it to this system and ask again about the purity of some subsystem of my radiation now in my brane perspective. And what I find if I do this is that initially the function or the plots here look very much the same. I start with high purity and then I go down as 1/2 to the m. But in the brane perspective, my purity stays low, essentially because if I choose the whole radiation subsystem, it's still maximally entangled with the black hole interior. And so it's still not a pure state. The question then again becomes, well, can I define maybe some wormhole purity somehow, which solves my problem and correctly reproduces the purity of a subregion in this in my boundary perspective. And in fact, I can do this, and the definition is very similar. Instead of just considering the purity of the subsystem A. I consider the purity of the subsystem A union I, where I is some subregion of my black hole interior, and then I minimize the purity over all possible choices of my black hole interior. Now, why would I call this a wormhole entropy? Because it shares certain features with sort of wormhole computations in Euclidean gravity, and in particular, that the purity of rho A union I here can be written as the trace, or can be written as a trace of what I call rho tilde A comma A, which naively you would think, okay, that should be like a factorizable state. So that should be the trace of, or like not factorizable, like trace of rho times rho. But really, we can create this state by taking the density matrix in our brane perspective of rho A union I and rho A union I, and then tracing over I, and so gluing together, if you will, the black hole interiors. And if we do this, the upshot is I just, to not exactly, but to a good approximation, reproduce the purity in the radiation subsystem. Okay, so let me just go to the last comments I want to make. First question is, can we extrapolate those results? And also we've discussed a bit about the double holography and those qubit models. So what, if we take this seriously, what does this teach us about semi-classical gravity? And the extrapolation would naively go by taking the brane perspective and sort of saying, well, the brane perspective really is like semi-classical gravity here. And the reason is that, for example, we have to use the island formula to produce the page curve. And on the other hand, that if we just compute naively the phenomenon entropy, the entropy, say, of a bath coupled to a black hole just grows without bound. And then the boundary perspective would sort of play the role of, like a true quantum gravitational theory. It really serves as a microscopic definition of our system. The page curve can simply be computed by computing this usual phenomenon entropy. And one thing that's also goes together really nicely with sort of intuition people have developed over the years is that semi-classical gravity in the bath is related to the well, yeah, you can obtain observables in semi-classical gravity, at least here in the bath, by coarse graining your boundary perspective. And one example was, for example, the phenomenon entropy. And so if I sort of repeat this intermediate summary I had now in this language, right, then the story would be that there's really two dual descriptions. One side of this dual description is some low energy quantum gravity, and the other side would be semi-classical gravity. And they're not related in the sense that semi-classical gravity is sort of like a strict approximation to quantum gravity in low energies, but really it's related by some non-local rearranging of information of freedom in a way that simple information stays where it is, but complex information gets shuffled around. For example, the outside of a black hole, then, or the radiation outside the black hole looks like a coarse-grained version of the quantum gravitational true state, but in fact, this information is not lost in the semi-classical picture. It's rearranged and it's used to reconstruct the black hole interior. Right, and so the question then is, well, in sort of like real life, what could those theories be? What are their properties? Low energy quantum gravity, I guess the guess you would have is that it's some sort of fundamental low energy string theory, which is good to answer questions about exponentially complex observables, but you might pay a price, for example, that like in the boundary perspective where I don't have a gravitational region, maybe I don't have a black hole interior. On the other hand, information is contained in Hawking radiation. And then there's this dual frame, semi-classical gravity, where information never leaves the black hole. Whatever I throw in stays in there, and I have no access to information just by having access to the radiation. Okay, yeah. I hope that was clear. I think there's sort of many different ways one can sort of refine these arguments and avenues to go on. clearly one thing that needs to be done is to expand this dictionary between the boundary and the brane. I've shown you two examples of, I've shown you two computations or two dualities, which is the phenomenon entropy in the boundary perspective is dual to the island entropy in the brane perspective, and the phenomenon entropy in the brane perspective is dual to the simple entropy in the boundary perspective. And then, but there's deeper questions or more questions, right? Like if you talk about the RT formula and so on, what are the limits if I want to apply this to the brane perspective? Also, the qubit toy model I've shown you could use some refinement. Can we sort of introduce time and then really explain how pair creation in the semi-classical picture at the horizon translates to emission of information in the boundary perspective? One thing I'm personally kind of excited about is double holography seems to be a way of addressing conceptual paradoxes people have pointed out. So for example, the frozen vacuum problem is usually used to argue that something like black hole complementarity cannot really be true, but double holography really is, double holography suggests that black hole complementarity is true, and in fact is some sort of like instance of some instance of black hole complementarity. And so studying the frozen vacuum problem, say in this concrete model, might yield some insights. And then of course, the last, and that's the really big question is, can we sort of identify these quantum gravity duality frames in more realistic theories and also show that they're dual to semi-classical gravity? The most naive thing you might want to think of is that, maybe type 2B string theory and type 2B supergravity, or like low energy type 2B string theory and type 2B supergravity really have this dual relationship, but that seems to be really hard. Maybe something which is easier achieved is Liouville gravity plus a 2, p minimal model, which in the p goes to infinity limit is JT gravity, and Liouville gravity plus the 2, p minimal model. Well, people believe that this is sort of a UV definition of JT gravity, so maybe one can make some progress there. All right, thanks a lot.
Thank you very much, Dominik. It was a very interesting talk. I think we can still take a few questions if people are keen. I can start. So at no point in your discussion did you make any comments about the dimension of the ADS spacetime that you're thinking. But if I remember, you mentioned something about any obstructions in higher dimensions, but I'm not sure if I misheard what you meant.
Yeah, no, the nice thing about double holography really is that there are no obstructions in higher dimensions. So, right, like a lot of work is usually done in JT gravity. But then it's not really clear, right? I mean, there's this paper by Sarachenko in Stanford where they argue that JT gravity is really an ensemble average over single Hamiltonian theories. But people usually don't like to take this lesson and carry it over to higher dimensions because it's not really clear what ensemble average, like what an ensemble average of n equals to 4 super Young nodes would be. However, here in double holography, this, at least at the level I was discussing it, so if I introduce end of the world brane and so on, that really works in any dimensions. Now you might say that, well, this end of the world brane is like, what is this even? Like, what's this object? And of course, this is a toy model really for more convoluted stringy constructions or supergravity constructions. But the point is there are these constructions. So for example, you can build spacetimes which are dual to BCFTs very explicitly in n equals to 4 super Young mills coupled to some boundary degrees of freedom.
I see. Okay. Any more questions?
Yes, I have one. Can you elaborate more on this frozen vacuum problem and like what do you mean that this double holography can solve such a paradox? So
Right. So the frozen, very roughly speaking, the frozen vacuum problem. If you have a map which sort of relates, excitations or like your Hawking radiation, the frame to information in the interior of the black hole, then you won't be able to excite particles at or near the black hole horizon, visible to an infalling observer. And the reason for this problem or this paradox, at the end of the day, how do I explain this? Yeah, the reason for the end of the day is that you need to pick a state which maps to the vacuum near the black hole horizon. But the question is, which state do you pick, right? So, because at the end, if a particle escapes out of your black hole, and you have your quantum state of radiation, then of course, in the real world, this might scatter off of some dust particles in the universe. And now suddenly the state you had of your Hawking radiation, of the information you had in your Hawking radiation, gets spread over a much bigger system, right? It gets spread to your cosmic dust, or maybe there's another observer which makes the measurements, and so suddenly this information gets entangled with the observer, and then it's not really clear anymore how to define this map. How to uniquely define a vacuum and excitations on top of this vacuum. Essentially, you would have to have sort of like a self-correcting map, right? It's like, I know that a particular state of my radiation maps to a particular situation in my black hole, but now it scatters off of like the dust particle, and now my map needs to scatter this new state, including the dust particle, to the exact same state in the interior of my black hole.
Yeah, I don't know much about this problem, but I get your idea. Thanks.
Yeah, maybe just let me add one more point, right? It's like double holography really gives you this map somehow, right? I mean, for double holography, it kind of works, and the map essentially just consists of how bulk information is encoded in say the bath using different homology, and so I would think that like analyzing this in detail hopefully teaches you something about sort of like where the argument for the frozen vacuum problem goes astray somewhere.
Any more questions? Well, if not, then let's thank Dominik again for the very interesting talk.
Thanks.